It's my pleasure to introduce for this last plenary lecture Eva Nogales from UC Berkeley. And Eva is, of course, a very well-renowned electron microscopist who's worked on many things, but I think, correct me if I'm wrong, but her main topics are transcription, and she's published recently some amazing work on the pre-initiation complex in transcription. And the second topic she's very famous for is what she's going to talk about, microtubule dynamics and the cryo-EM perspective. So please, Eva.
Thank you. So I thought, many of you may not be interested in microtubules or dynamic instability, but I think it's a nice example of how, in the pursuit of some biological insight, where electron microscopy was the obvious technique of that could be of use, how this particular project has evolved with the field. How, in the, as Elena will call it, the prehistoric time, what it is that we could do to study tubulin and to study microtubules, how things evolve as cryo-EM was getting better, and then this revolution in resolution that we've seen in general, how it affected our own studies of microtubules. So I'm going to remind you of the player, the main player, which is the alpha-beta tubulin heterodimer. This is an amazing protein that has this capability to self-assemble. It self-assembles head to tail, making linear protofilaments, and then these protofilaments associate laterally, and they do it with a certain stagger and curvature that ultimately gives rise to the cylindrical shape of the microtubule. Now, the structure is, I think, is very beautiful, but the thing that is amazing and unique about microtubules is that they are a dynamic polymer. They undergo this process known as dynamic instability, discovered by Mitchison and Krishna, by which they are able to switch between phases of a slow growth and very rapid depolymerization. And this is a video from Gary Boris's website showing this at the edge of a cell. And this is a process that you can reconstitute in the test tube. You just need purified tubulin and a source of energy, which is GTP. Now, why these dynamics? And this is because microtubules have to have the capability to reorganize very dramatically through the cell cycle. So again, this is, in this case, borrowed from Conley Ryder, and it shows in fluorescent microscopy how the spindle evolves to align the chromosome in metaphase and then separate chromosomes. And this requires the microtubule cytoskeleton to be reorganized structurally and then to depolymerize, because this depolymerization is going to be coupled to the movement of chromosomes. And it is absolutely required for this reorganization that the microtubules are able to break apart and reform. And in fact, if you mess up with this dynamic character of the microtubules using small molecules that stabilize microtubules, you stop the mitotic process, and ultimately cells commit suicide. And this is the reason why drugs like Taxol is very broadly used in cancer therapy. But so the thing that is interesting to us is that this metastable behavior, non-equilibrium behavior, is driven by energy consumption, and this comes from the hydrolysis of GTP. So tubulin is a GTP binding hydrolyzing protein. This is the structure of the dimer, and there's two nucleotide. Beta tubulin is always going to be blue and alpha green, and the nucleotide that binds in alpha tubulin at the end site for non-hydrolyzable nucleotide, this is put in there during the process of biogenesis of the dimer, and then it just remains there, is not exchangeable, is not hydrolyzable, and is trapped at the monomer-monomer interface within the dimer. But this is the site of action. This is the E site for exchangeable site. It's in beta tubulin. And this one is exposed when tubulin is not assembled. And it can very readily exchange with GTP, which is, of course, much more abundant in the cytosol. And this GTP-loaded dimer is the one that can very effectively add up to a growing microtubule end. But this is the trick. So now, when the next subunit come about, it makes new contacts at this newly formed interdimer interface between alpha and beta, and there are residues in the alpha subunit that catalyze GTP hydrolysis. Okay, so exchange happens in the unit, and hydrolysis happens within the lattice of the microtubule. And this coupling of assembly and hydrolysis is what gives rise to dynamic instability, because in a GDP-bound state, the microtubule is unstable, and it will come apart. And already Mitchison and Krisner, which discovered this phenomenon, proposed a model. It's called the GTP cap model that has held through the years. And the idea is that the microtubule will keep growing for as long as it contains GTP-bound subunits at its end. But if those are lost, then the whole lattice underneath will disassemble. So GTP hydrolysis is required for disassembly. If you use a non-hydrolyzable GTP analog, you form microtubules fine, but those are stable and do not undergo this dynamic instability. So we don't know the precise structural nature of the microtubule end when it's stable, because every microtubule end is different, and it's been very hard to really visualize. And so the precise nature we don't know. So I want to show you an animation that is just an approximation, just our imagination, but so that you see very visually this coupling occurring at a point when the lattice, this GTP cap is going to disappear. And the whole point is that this situation now, with no GTP in the exchangeable site, is completely unstable, and it falls apart. And the falling apart has been visualized many times, occurs through the curling and peeling of protofilaments. So we are interested in why GTP hydrolysis results in this instability of the microtubule, which in a structural biology's words is stated as what is the effect that GTP hydrolysis has in the microtubule structure. And to answer this question, of course, you need the structure of tubulin in the microtubule in different nucleotide states. And the structure of tubulin was difficult to obtain, and cryo-EM and the study of microtubules was an obvious alternative to crystallographic studies. But the way we went about in the 90s to get a first glimpse at the structure of tubulin was to use an aberrant polymer of tubulin. So tubulin has this amazing tendency to self-assemble, and in vitro, depending on the buffer conditions, can make different things. And one such thing was found in the 70s, is that in the presence of zinc, instead of the protofilaments, instead of associating in a parallel fashion, they bind like this. We know now that it's because the zinc binds right at a contact, lateral contact. And now one is going up, one is going down, one is facing you, one is facing me. The result is there's no curvature. This grows in 2 dimensions. And, that means it's like a 2-dimensional crystal. And at the time, in these prehistoric times that Elena was referring to, the only PDBs that came from electron microscopy were those of 2D crystals. Using the methods that had been developed by Richard Henderson at the MRC with bacteriorhodopsin, and then used also by others. So came down in, Sharon Wolf and myself in Berkeley used those crystallographic methods to obtain the structure of tubulin, and this was polymerized tubulin in protofilaments, but that were associated in this aberrant manner. And this is a polymer that behaves very much like microtubules in many respects. It also binds taxol and is also stabilized by taxol. So this structure was also one that showed us the binding side of this important anti-cancer agent. But of course, this is not the microtubule. This is an aberrant state. And at the time, a number of groups were studying microtubules, and the resolutions were in the 20s, 20 angstroms or so. In fact, the best one at the time we obtained the structure of tubulin was that of Ron Milligan at 20 angstrom resolution. So we took that map, and Ron had pioneered the use of hybrid methods in the studies of actomyosin. So we used the same principle, take the crystal structure, and in this case of the whole protofilament, and fit it within the low resolution EN map. Of course, this has been done millions of times now. And the resolution was enough that with the asymmetry in the shape of tubulin, we actually did, in retrospect, a phenomenal job. And this told us what in the tubulin was facing out, what was facing in, and approximately the regions that were making lateral contact at kind of very low resolution. So this was okay, but we have this structure, and this is as good as we were at that point. And about 2 years later, the first of the many to come X-ray structures of tubulin was published by Marcel Nosseau, and this they use the same trick that had been used for actin, which is you stop it from polymerizing, which will inhibit crystallization by binding it to something that inhibits tubulin assembly, and in this case was both a small molecule as well as a factor, a cellular factor that has as a role in life to actually sequester tubulin subunits. So in this structure, there's two dimers, and if you compare them, there's a curvature. This was extended even in the crystal. There's a curvature to it. So that, at a very coarse level, was interpreted as, this structure in the straight protofilaments of these zinc-induced 2D crystals is a surrogate of the structure of tubulin in the microtubule, and this curve state is a surrogate of the free tubulin that is seen in peels of protofilaments during disassembly. That means that when we compare to see what is the conformational change that happens during disassembly, okay, when the GTP cap has been lost, going from a GDP in the lattice to a GDP free from the lattice, we could just compare the two structures, okay? And this is a comparison for the beta subunit, where the N-terminal domain that binds the nucleotide is superimposable, is shown in gray, and there is a second intermediate domain that really moves, and it's very obvious. It goes from the orange in a polymerized state to this light purple when it depolymerizes. So this is quite significant, and if you see it, if it happens for many subunits in a row, it has the kind of microscopic effects of this peeling process. But this is not the change that I was telling you about. The change that we wanted to describe are the ones that happen within the microtubule upon hydrolysis, is the change from here to here, okay? So the red to blue, we don't really know at a structural level what it is. And to describe that, we really needed high resolution of the microtubule itself, and it had to be in different nucleotide states. And from the structures of the late 90s and early 2000 at 20 angstrom resolution, there was a progression, especially Ken Downing really pushed it. But we got stuck at about 8 angstrom, and we couldn't go farther. And we knew that these changes have to be settled, okay? Because the tubulin is constrained within the lattice, so they have to be small, but we want to be able to describe them because they are at the heart of dynamic instability. So some brave souls in my lab decided that they were going to pursue this. At the time, Ed Egelman had created this beautiful software for real space reconstruction of helical structures, and I'll show you in a second microtubules are truly not helical, but we decided to use that kind of approach, adapted for the microtubule, using huge amount of data, just kind of brute force on a great microscope, a Titan, but not a Krios, so something with a Gatang side entry, no automation. At the time, this was a microscope that was being used by Bob Glaser for development of faceplates, so it was a very unique and hard to use. And we had to collect the data on film. This is why I showed this image. Some of you in the audience will never know what this was, but we have to spend time in the darkroom. Because at 300 kilo electron volts, CCD cameras are just terrible. Okay, so in this method, you basically segment your polymer with boxes that are overlapping, and then you just treat those as if they were single particles of, pre-initiation complexes or ribosome or spliceosomes. Okay, so many images like this, you get all the pieces, and now you find the relative orientations, and you use an approach like single particles. The problem is this. You may have noticed that there is something unique in one place in the microtubule. So most lateral contacts between protofilaments are homotypic in nature, meaning the beta subunit interacts with beta and alpha interacts with alpha. But there is a unique position, which we refer to as the seam, in which this breaks down. And now beta interacts with alpha and alpha with beta. And that means that if I have a piece of an image of a microtubule and I want to align it to another piece from another micrograph, I have to align the seam, because otherwise I'm going to be mixing alpha and beta tubulin. And I want to describe the microtubule in great detail. I cannot be averaging those two proteins. The problem is that alpha and beta tubulin are very similar. And if you start with your raw images, there is very little signal to differentiate them. In reality, when we're looking at these things, they look more like this. Okay? So in order to not mix alpha and beta tubulin, we need a fiducial. We need something that marks the dimer, that differentiates between alpha and beta. And this is easy because there are zillions of proteins that binds to tubulin, and they do it with precise stereochemistry. So they recognize alpha and beta tubulin. And we just use one of those, okay? One that has been studied a lot, which is kinesin. Kinesin is bulky. It binds in the middle of a tubulin dimer. And now, you know, it's going to be very obvious where the seam is, because these are at a certain distance, and suddenly there is a jump. So if you look at an image of what we call undecorated microtubules, it means with nothing bound to them. This is how they look. If you put kinesin in excess so that it binds to every single site, I hope you can see these knobs. You can see them by eye. So the software does a very good job at aligning them. And we can rely on these to localize the seam and align alpha and beta tubulin. And doing that, we move farther. So in that way, we're not imposing helical symmetry, because we can't. But still, a microtubule has many copies of a protofilament. So this is an example. It's 14 protofilament. Microtubules can grow with a range of protofilament numbers in vitro. So what we would like to do is to be able to average the protofilaments, just like when you have 4-fold symmetry or 6-fold symmetry or whatever. So what the idea, this I'm going to demonstrate graphically, is you take this structure and you rotate it and translate it following the helical rules of the monomer, if you want, if you ignore the difference between alpha and beta tubulin. And when you do that, now in here, you will have added up the signal from two protofilaments, and that will boost up the signal-to-noise ratio. But of course, when you do this process going through the seam, this protofilament gets all messed up, right? If you do this one more time, now in each one of these, you've added density. You're progressing in your averaging, but now you have two bad protofilaments. Well, I just keep going, and when I've done these 13 times, in this position, I have the average of 13 protofilaments, and this is now great. It's going to have higher resolution. The rest are bad. I don't care, because we work in real space, so we can just go mask this protofilament out. If I'm finished, that's it. But if I want to now recover the microtubule structure, I just use the symmetry that I know it exists. I know where the position of the seam is, and I just reproduce it. And this is something that we're doing cyclically through the iterative process of improving the resolution through the normal iterations. Okay, so this way we were able to finally push the resolution. This is the joint work of Greg and Gabe, which collected this huge data set and developed a pipeline. And they broke this 8 angstrom resolution limit, going below 5 to about 4.7. And this, it was encouraging because we were starting to see turns of helices and things like that, but it was not enough to still do modeling. So we collecting data set for different nucleotide states, and then we work with David Baker, and we use Rosetta, this protein prediction model with the constraints of the map to be able to generate models. I'm not going to show them to you because this is 14. This is about when we were getting the new detectors. So I'm going to, detector era kicks in here for microtubules, and with 20 times, not 2 times, 20 times less data, this is what we got. Okay, so this is what we are used to seeing now. This is 3.5 angstrom resolution, and at this resolution, this is very nice. You can follow the polypeptide chain, and one of the things that we could do now for the very first time for microtubules was to describe the details of the lateral contact, which ended up being much smaller than we had thought. It's basically a kind of lock and key mechanism where an aromatic side chain nestles against a pocket made by two loops in the adjacent subunit. Okay, so this was great. We finally had close to atomic, or this kind of resolution for microtubules, and we went and to answer the question that we were interested in: what happens with nucleotide hydrolysis? So we made microtubules with normal GTP that gets hydrolyzed to GDP, so I'm going to call that the GDP state, but we also made them with GMP-CPP, which mimics a GTP state, and with GTP gamma S, which we found out mimics, we think, something that is closer to a GDP-PI state. So I'm going to show you what happens. And this is actually the 2014 pre-revolution map, but we made this nice movie, and it's still very useful. So this is one dimer, this is the other. I'm looking at the microtubule from the inside, and this is where the nucleotide is hydrolyzed. So I want you to just look at that. The change is settled, but hopefully you can see that this thing is moving up and down. So this side around the nucleotide is compacting. I'm going to show you now that in more detail with the models that we're generating from the high-resolution maps. And I'm just taking this protofilament with these two dimers and turning them around 90 degrees. So this is the surface on the outside. This is the bumpy surface on the inside that we're looking into right here. And these are the two structures superimposed on this dimer, where the orange is the GMP-CPP, so the GTP state, what we should mimic the GTP cup, if you want. And the alternating blue and green are the normal dynamic microtubules where GTP has been hydrolyzed. So if you're looking here, so you look at this, and this is what I was telling you about. It looks like a compaction, like the dimer is coming down. It is not true. It's just a deformation of the alpha subunit. So the beta subunit doesn't change. There's a small change in the loopers around the nucleotide, but very, very little. But the alpha subunit does change. There is a region of the molecule that is actually crunching in. Is the alpha subunit that is compacting and then going down against the nucleotide. So I'm going to run this, which is just an interpolation in chimera. It's not molecular dynamics or anything like that, to show this kind of compaction. Is settled. Is a movement of 2 angstrom. And it happens to show you that there is a deformation of just coming down. We call this the anchor point. This point doesn't move, but this point does. And this is through the scrunching, if you want, of this domain against the rest, resulting in a compaction here and this kind of compaction of the full lattice. But the motion, this is the motion that the alpha subunit is undergoing. Okay, so our proposal is that this is generating a strain where the alpha subunit is really on a state that is like a spring that you have pressed on and that really wants to be released. But of course, the other thing that can be affected by nucleotide state, the more obvious you would think, are lateral contacts. And again, we now have pretty good resolution for these contacts. This is the one that I showed you before between alpha subunit. This is the one in beta, is similar, but here we have a tyrosine instead of a histidine. So if we look at these contacts in different nucleotide states, what do we see? No changes. So at this resolution, at 3.5 angstrom, there's no changes between nucleotides. Okay? So the idea that we have is that the energy of binding in the lateral contacts is maintained, but what you have is growing strain, and that in a GTP state, the lateral contacts are happy holding the protofilaments, but when this compaction in alpha tubulin happens, there's now a strain, this tendency to want to bend, and these lateral contacts now cannot hold it together and let go. Okay, except that I'm showing you homotypic interactions. But there is this particular place, the seam, which, by the way, what the heck is it? Why does it exist? Because it's really present there. It is, nature has selected it, so it must be doing something, and we don't know what it is. So because now the direct detectors are so good and we have so much signal, if we don't do the symmetrization that I was telling you about, and we just work with the unsymmetrized, or C1 if you want, where we do see the sim, then we should be able to see what is special about that lateral contact. So, so even without symmetrizing, we get very close to, around 3.94 angstrom resolution. So if you look now at these heterotypic contacts, they are very similar. Okay, so this in green is the alpha-alpha, and here is the alpha-beta. And what happens is that these loops are at a slightly different position, so this is just not quite optimal. And the same happens when you have, instead of a beta-beta, a beta-alpha. And what turns up is that this effect is actually macroscopic. So I'm going to show you something that I have to explain, but I'm going to use it a lot, so it's worth the time. So this is looking at the microtubule from the top, so you're looking in principle at the cylindrical shape of the microtubule. And what is displayed here is the RMSD for the alpha chains in tubulin between the symmetrized and the unsymmetrized map. Where in the symmetrized, we are assuming that there is true helical symmetry and that all the subunits are in equal position with respect to this cylindrical shape. And when we do that, they look identical except for one point. And this point happens to be the sim. I'm not showing you the kinesins, but we have the kinesins there all the time, so we know exactly where the sim is. Okay? And this, I'm going to exaggerate it, but if the protofilaments are going around the cylinder like this, and there is this certain angle between them, is going like this. And this is by about 3 degrees, and is a movement of about 2 angstrom. But it's enough that it makes us think this is maybe a weak point in the microtubule lattice. And the thing that is interesting is this is the normal dynamic microtubule. This is GDP. If we look at the GMP-CPP, is it any different? And you say, no, it's not any different. Yeah, it's just we did this to trick the audience. This scale is different, because if we use this scale, we see much less difference, okay? So in a stable state, this displacement from the cylindrical shape, which means that that contact is looser, is reduced. So it is possible. This is just in our minds right now, that this is the point where the lattice starts breaking apart. That when this tension builds up, is the first one to peel off, and then the rest now peel. And we don't have a proof for that, but I'll show you something that points to, at least is not against it. So, better than nothing. So, of course, we have this pipeline now to get relatively good resolution of microtubules, and now we can look at many things. One of the things that we can look at are antimitotic drugs, okay? This is important. We all have the vision that one day this methodology is going to be useful for drug screening and things like that. So Liz, Nisreen, and Stewart look at three drugs, one bound to the microtubule. And one is the Taxol that we had already studied in the context of these aberrant polymers. The other one is zampanolide. So this is a different molecule that, however, binds in the same pocket. This is a view from the inside, and this is a pocket that exists in the alpha subunit. We're looking at it from the inside. So zampanolide binds in the same place, but it binds covalently. So it's interesting in that way. And then this is another one. They are all microtubule stabilizing drugs. This is called peluroside. This one comes from the Pacific yew tree. These are all natural products. Zampanolide and peluroside, they both were extracted from marine sponges. And this one we actually get from Peter Northcote in New Zealand. This is from a New Zealand sponge. And I think for a living, Peter goes snorkeling and picks up these things, these creatures, and then extracts molecules out of them. Have fun. In any case, we can look at these drugs and see where they bind, and it's enough resolution to orient them. There are crystal structures in this one, electron crystallographic structure. There are crystal structures of these by X-ray crystallography. They have better resolution, but in our case, we can see what they are doing to the microtubule. because in the crystal structures, they are in the context of these inhibited, non-polymerized structures. And remember, these bind to microtubules and stabilize microtubules. So I'm just going to talk about this one, pellurocyte, because it's interesting. This is a view from the outside, and I hope you see that it's binding between protofilaments. And given that it binds to protofilament, the question was, does it bind to the seam? And in this case, again, we use the non-symmetrized, so the resolution is worse. In this case, I left the kinesins to see that we really know how to paint blue and green because we know where the kinesin is. So this is bound to a homotypic contact, and this is bound to a heterotypic contact. So it does bind across, and if we look at the details, these residues that are interacting with it happen to be conserved between alpha and beta tubulin. So what effect that these have now in this opening that I was telling you about, if we now compare the symmetrized and unsymmetrized structure for these microtubules, that has gone. So this is a stapling between lateral contacts, stabilizing the lattice, and is doing it also at the seam. It may be just a coincidence, but maybe this is part of the mechanism. And by the way, if I compare the same microtubule in the same nucleotide state with and without pellurocyte, we see this thing. So this is what pellurocyte is correcting, these 3 degrees of opening, if you want. By the way, so pellurocyte is regularizing the lattice, but that is not necessarily the means by which these drugs stabilize microtubules, because Taxol does the opposite. Taxol is a mess, and we use it a lot. We used it for a long time to do cryo-EM, because then you stabilize your microtubules. You don't have to worry about them depolymerizing during all your sample preparation. So getting high resolution with Taxol microtubules is much harder than doing it with anything else. And we couldn't understand it. We're getting bigger and bigger data sets, and we're not going anywhere. And it ends up, we use Reliant to do sorting. These are just 2 classes. And in the context of this difference that I was telling you about the seam, these are very large. There are total deformations all around the microtubules, and they come in all ways. We cannot just classify it and improve the resolution. This is really like a continuum. So Taxol, we think, is relaxing the strain that normally wants to peel the microtubules, and now lateral contacts don't have that kind of turgency, if you want, that comes from the protofilaments trying to peel apart, and they're wobbly. Okay? By the way, if you bind both Taxol and pellurocyte stabilizes, they have additive effect. It's not only that they bind in different sites, it's that they use different methods of stabilization, and now you get a microtubule that is perfectly regular, doesn't have this opening at the seam, and is double stable, if you want. Okay, so 2 different drugs are doing different things while stabilizing the microtubule. One binding there, closing this seam, the other one just relaxing the requirements for these lateral contacts to be well organized. Okay, so we think that we are on the way. Hopefully the resolution will get better to be able to visualize the binding side of drugs, and in many cases to orient them sufficiently that it will guide us to what they're interacting with and what chemical modalities are important for the interaction. But of course, we don't, apart from the pharmaceutical interest, there are myriads of proteins that interact with microtubules. In some cases, like kinesin, they're using it as a railroad track to move things, or to be positioned in the cell. Many are acting on microtubules dynamics and affecting the dynamics, or organizing the microtubule's cytoskeleton. So now we can use this pipeline to study all of those. And I'm just going to show you a number of examples. From the poster winner, there's a lot of work that is being done with kinesins, both motiles and kinesins that depolymerize microtubules. So I'm going to show you 3 examples. One is of an EB protein. I'm not going to go into the details. These are called plastic because they track with the growing microtubule end. They're used by cell biologists a lot to visualize microtubule dynamics. And the idea is that they are binding to the GTP cap or to some region that is unique in terms of nucleotide state and structure in the microtubule. I'm also going to tell you about PRC1, which is a protein that organizes the microtubule in the spindle. It cross-links them, and it makes anti-parallel bundles. And I'll go through this fast because these are published, and then I'll spend some time on an unpublished molecule, which is TPEX2. So from the point of view of cryo-EM and the difficulty of studying this, by the way, once we start looking at proteins that we are interested in looking and seeing bound to the microtubule, we don't need the kinesin anymore. In fact, we want the kinesin out of the way because it may compete for binding to tubulin with these things, okay? So until now, I was not showing you the kinesin, although it was there. Now I'm not showing it because it's not there. I'm showing you what it is that we're binding. Now, each one of these, you're going to see, is smaller and smaller, meaning that the fiducial that we use for our alignment is getting smaller and smaller, and we really rely on these very high-quality images and of procedures that we have used to maximize, to optimize the alignment of the seam by assuming that, in principle, our method is giving us some kind of local minima, but then exploring the possibility that the seam is not exactly localized, and do another round of cross-correlation. I'm not going to get into detail, but the whole point is you'll see that we can do smaller and smaller things. And I'm not going to show you today, but it has gone to the point that if we have really good images, we can do it with nothing. Okay, so alpha and beta tubulin are really different at this resolution, more microscopically by an extra loop in alpha tubulin, which in beta tubulin is where Taxol binds, by the way, and we can do it now with nothing in it. But this has taken really a lot of optimization. So EB, the particular form that you use is human EB3. This is where it binds. So this is one dimer, this is another. And this protein uses a chalconic homology domain to bind right between 4 dimers at the intradimer and interportofilament interface. This is where we see this compaction. If you wanted to have something that binds and is sensitive to whether tubulin is bound to one nucleotide or the other, this is where it would be. This told us a lot. I'm not going to go into detail. This affects dynamics in a double way. It facilitates assembly, and then it facilitates disassembly. And the structure actually demonstrated how, by being sensitive to this state, recognizing a particular compacted form, and actually inducing hydrolysis. But I just want to show you, because this is a structural meeting, there was a crystal structure of EB3. This was in part why we chose it. It's very well behaved biochemically. Oh, now I went past. Sorry, it just didn't respond. There's a lag. Okay, so there was a crystal structure for EB3, so we could actually start with that and then refine it into the structure. In general, we didn't have to do many changes. The important thing is that now we were seeing it bound to the microtubule. There was one exception, and it's this loop. This is a loop that in the crystal structure was involved in crystal contact. It is actually, in normal life, is involved in contacts with tubulin, and that one has to be retraced. And this is you'll see that kind of idea repeating a few times. Okay, so this is an example. That chalconic homology domain is about half the size of a kinesin motor. This is PRC1, is a larger molecule, but the domain that binds to a microtubule is a spectrin domain. It's just 3 helices, okay? And it binds in the middle of the dimer in this case. So something that you don't expect to be very sensitive to nucleotide state in the microtubule. And it isn't. And is, so there was one thing in the crystal structure that had not been resolved because it was distorted, and it was this loop. And guess what? This is the loop that interacts with the microtubules, and we could trace it, and we could see this key arginine that is involved in contact with the beta subunit. And there's more contacts, but I'm concentrating on this one because this is part of the contact that is used by kinesin. They have similar, one large and one smaller footprint, but this is just to show you that if you it's a different view, that is, you superimpose the structures, they use the same arginine to interact with the same region on the tubulin structure. So these are two completely different molecules, structural motifs, that are interacting similarly and using a similar pocket within the microtubule. And this is interesting because it can go the other way around. I'm not going to show you, but a chalconic homology domain is used also by kinetochore complexes that bind to microtubules. And we've also studied those. And that chalconic homology domain not only doesn't bind like EB3, it uses a completely different surface on the chalconic homology domain, and it binds in a completely different part on the surface, which is great for us because it means if someone discovers a protein and it has a certain domain that has already been seen in a microtubule-associated protein, it doesn't mean that we can guess how it's going to bind to the microtubule, so we can do another structure and get another paper. So I'm going to tell you the last story. This is the unpublished results. And this involves a protein that is involved in microtubule nucleation. And there's a number of ways in which microtubules can be nucleated, but one of them that is very important during mitosis, it depends on what is called the run-GTP gradient. And it involves nucleation that happens close to the chromosomes, where run bound to GTP is high, so that microtubules start there and emanate away from it. And the way this happens in a run-GTP manner, so in this localized manner in the cell, is that when run-GTP is so in conditions where run-GTP is low, then TPEX2 is sequestered away by importin. So you hear of importin in the context of moving things in and out of the nucleus based on run-GTP gradients. But it's also used in this way. So TPEX2 is bound to importin. It is sequestered in the nucleus during interphase, and then when nuclear breakdown occurs, if it's near the chromosome where run-GTP is high, now this is going to fall off. The importin is going to fall off, and the TPEX2 will be freed. And this freed TPEX2 now bound to microtubules, and by some means is able to promote nucleation and growth of microtubules. So this protein is pretty large. It has a lot of regions that are predicted to be unstructured, and the nuclear localization sequence and the importin binding site had been identified. Now, Tom Surrey has done a lot of very nice reconstitution studies, and he has found that TPEX2 binds preferentially to microtubule growing ends and prefers GMP-CPP microtubules. So this is another protein that is somehow detecting the nucleotide state of tubulin inside the microtubule. Now, this protein is a little bit hard to work with because it has a tendency to bundle microtubules and to misbehave, but Thomas' lab was able to generate a construct, a smaller construct that they call TPEX mini, that still retains this kind of behavior, which is the part that we're interested in. This has to interact with many other things, kinesins, Aurora A. So we concentrated on the part that has to do with this microtubule behavior. So the idea was to take this TPEX mini and put it on GMP-CPP microtubules and look at it. And this is how it looks. This is, again, work with by Rui. And the only thing that we see now is this tiny little helix here and this extended segment. And this part is, again, this is one dimer, this is another, is binding between alpha and beta across dimers and protofilaments, and this is binding from one protofilament to the next, so also across protofilament. And these are two very small regions that are connected by a flexible linker. You can play with the threshold to see that there is some density there, but of course, at high resolution, it blurs away. So we refer to these structures as the wedge and the ridge. If I turn this around, so the microtubule will be going like this. This is the wedge. It really is wedging between two protofilaments, and this one is in the very, very crest, the very ridge of the protofilament. So that's the names. So the resolution here is 3.3, and just based on the position of big side chains and structure predictions, we proposed, but we weren't 100% sure that this is the mini and this is the structure prediction, that they corresponded to those regions. And those would be interesting because that happens to be the regions for importing binding, meaning that if these, we don't have to invoke any weird allosteric or weird mechanism. Importing is binding to the site that interacts with the microtubule. So it's really plugging the interface, and it has to go for this to be able to bind. So we asked Thomas to generate a construct that now we call micro, which is significantly smaller. And the question is, do we still see the same structure confirming our model? And the answer is yes. We see the same. The resolution is a little bit lower only because we had less data. And in fact, now we have generated a model. We're pretty confident because we've gone to the point of generating point mutants that really lead to this protein falling off the microtubule. So in particular, this, for example, this is a key phenylalanine that if we mutate to alanine, just the protein loses affinity for the microtubule. So I know you may not be interested in microtubule dynamic growth, but I think we've learned a lot from this structure, okay? So this is, to start with, this is a unique way of binding to the microtubule. So we have another thing that interacts across protofilaments and dimers. But in this case, instead of being a globular domain that has a very defined binding pocket, is two little domains that are connected by a flexible linker. And we think that this is very important. So the structure has first told us how the run GTP controls binding of TPEX2 and function of TPEX2, because it really is occupying the binding site that is required for binding to the microtubules. And we think that this binding across dimers and across protofilament, but with a flexible linker, means that this protein can bring together and facilitate the coming together of the tubulin subunits, even in very early stages in the nucleation process where you don't have a fully closed cylinder and there are different levels, degrees of angle between the protofilaments. Now, because of the wedge, and where it binds, it will be very sensitive to nucleotide state, and that's why it binds to the end of microtubules, but it does not bind to the rest, which is a compacted lattice. And although we don't have data yet to support it, but it's a hypothesis that we want to test, we actually think that the mechanism of action by which this protein promotes assembly and growth of microtubules is that it may be slowing down the compaction process related to hydrolysis, because by sitting the way it does, it's actually completely incompatible with a compaction of the lattice. Okay, so we don't think that it inhibits completely GTP hydrolysis, but it's enough to slow it down and give this assembly the chance to make something big enough that cylindrical, the cylinder closes and grows and establishes a GTP cap before it comes apart. So these are things to test, but they have come out from this direct visualization that really just 3 years ago seemed impossible, because we really needed the signal to drive this alignment that will not mix alpha and beta tubulin. Okay, so I mentioned the people, but I'm just going to do it again. So this initial work, the hard work with the film that had to be developed and all of that, was done by Greg and Gabe. Now they have both their own labs at Rockefeller and Scripps. Liz, Stuart, and Nisrin were the ones that work on the drugs and the PRC1. Stuart is now doing his postdoc at Leiden. And Nisrin graduated. He was a graduate student with Ken Downing, and she just had a baby, so she's taking a break for now. Well, a break. You know what I mean. Taking care of the baby. And Liz is a postdoc in the lab that is probably going to be in the job market by the end of the year, is now working on other microtubule binding proteins. And Rui did all the high-resolution structure with the EB3, the nucleotide estates, and the TPEX2, and now has his own lab at Washington University. And thank you very much for your attention.
Well, that was great. Thank you very much. Are there any questions, please? Yes.
Ava, that was absolutely gorgeous.
Thank you.
I have a practical question about the TPEX, because you said that it only binds at the ends.
Yeah.
And so, in fact, to collect the data, when these poor students had to take data only from the very tippy ends of microtubules?
Sorry. It binds to the end of dynamic microtubules that you can mimic using a GMP-CPP lattice. Sorry. Yeah. But this reminds me that, you know, right now we are mimicking the GTP cap using these nucleotide analogs. And what we would be fantastic, but this, you know, we have to think very hard. Like Elena said, you have to think. Which is a bother. So we have to think very hard, because what we would like to do is to start microtubule assembly on the EM grid, so that you have many microtubule ends, because right now, you know, we grow microtubules and you take these images and you saw it, we rarely see any end. And have dynamic microtubules growing, and start looking at those ends, and start seeing at which point the compaction happens along the length, whether there are, you know, transition regions and things like that. And it may have to be a combination of this kind of methodology and tomography, the kind of thing that Denis Chrétien is doing, but combined with this methodology. So it is a good point. Eventually, instead of running things in a more automated fashion, we have to think, and we have to do the real experiment that way. And then we will be looking at microtubule ends.
Hello, Amédée?
Yeah, Amédée.
So I saw in your cross-section with the RMSD that you had 14 protofilament microtubules.
Yeah. We've done this with 14 and with 13 protofilaments. It's the same.
Okay.
And the tendency is always the same. If you do 13 protofilaments with GDP and GTP, the GDP is that you know, breaking of the cylindrical shape is always larger in the more unstable GDP state. Yeah. Yes. Sorry.
I have maybe a naive question, because I don't work with helical. When you treat it as a single particle, so when you extract your fragments, because they overlap, you would have the same molecule present in several extracted particles.
Yeah. Yeah.
And the more they overlap, the more copies you have. So doesn't it lead to problems with reference?
No. This is what makes the process very robust. This is Ed's method. So every subunit just is so every box only, with respect to any other, only has truly unique a single layer. They're 80 angstroms apart. This method has really revolutionized. In our case, it's just kind of an intermediate because we have to do other things, but it has really revolutionized helical reconstruction methodology, because microtubules are relatively rigid in terms of bending. I mean, it is an issue going to high resolution, but there are ways to deal with that. But there are many other that are more flexible, that have more irregularities and things like that. And Ed's method, which always relies on this for signal, and it is relying on an underlying helical symmetry, okay? It works very robustly, and you do not have to worry about that. You have to decide which kind of repeat, which kind of overlap you have, and that relates to the helical repeat a little bit. But it does work very beautifully. And it's really part of what makes the algorithm work well.
Thanks for the fascinating talk. So I just wanted to ask a question about a hypothetical situation. You told about this deformation in the lattice and also this perfectly circular cylindrical shape that is distorted in your Reliant classes. So suppose now you know that, and if you have this pre-detector data, and if you reprocess it and take into consideration each and every deformation, is it possible that every data set that was taken 2-3 years back, and if you take into consideration all these deformation and computationally correct for them, you would be able to get high resolution from the low resolution data which you just thought couldn't be the atomic model?
Right. You know, the highest resolution is what we obtain doing the averaging. We only do this in order to get this additional layer of information. All of this relies on data that is taken on direct detectors. So, so we can process this. The information is utilized. So when the images are being aligned, any information that is there in the geometry of the system is contributing to the alignment. We may not have conceptualized it or thought about what it means, but it's in the data. So it is, even before we looked at it, it was contributing to the assignment of the seam, because it's in the images, right? We can use the methodology that we have right now, where we optimize that search of the seam with previous data sets. They will really work better and maybe give better resolution if they really are of the quality that we have right now. If we go to the film data, you know, I don't think it's going to add much more. I mean, that in particular was with kinesin, which really what we have optimized in terms of seam search, which is very, very important for the TPEX2 or for undecorated microtubules, are minimal, right? So, yeah.
Just to follow up the technical question, I think someone already mentioned, so related. Did you say that if you process the data today, you don't have to do all the tricks you have? A couple of years ago, you have this, you know, very smart idea of decorating things to create the more obvious signal.
So if the data is very good, we can go back, use the methodology that we've developed now, and we will do better, period. If the data is of the quality that we're using. Because our procedures have improved, yes.
So you don't have to do this decoration to enhance?
That's right. We don't have to do the decoration anymore. Yeah. There is, you know, from time to time, things fail. I'm going to make a disclosure. So we just published a structural comparison between mammalian microtubules and budding yeast microtubules. And there's some very interesting things, and it's just come out in JCB for the few microtubule people that are around here. I invite you to see it, because this is done a lot in the microtubule field when doing reconstitutions. You mix a lot. You get mammalian microtubules are very easily purified. So you use microtubules, and then you're using Xenopus egg, you know, Xenopus kinesin or EB from yeast or whatever. We do these mixtures. And in that paper, it shows that there are significant differences, and you have to be very careful. But one of the things that happens in yeast, we could never get to very high resolution, because we always have these populations of microtubules where it didn't seem that we were aligning the seam. And this is because in yeast, for whatever reason, you have multiple seams. So instead of just having one, you can have 3, or you can have 5, or if you go past that, you have a mixed lattice. But in yeast, I don't know about Pombi. And then our methodology, it can't work, because then you now, how many seams do you incorporate? So in that case, the resolution is a little bit worse, because we always have this mixture, and we can never really sort it out, but it's there. But it's interesting. Why do they do that?
So I have another question. Are you interested in trying faceplate data?
Oh, yeah.
So, because I just want to, but before you answer the question, I do want to make a point about someone who asked about whether you could go back to the old data. And really, I have this feeling that anything that's not taken on direct detector will sit in a drawer forever, because the direct detector really has revolutionized the data quality, and one can't go back. The film will never work as well.
No.
The CCD will never work as well.
Right.
And I'm wondering if we'll be saying the same thing about faceplate data in a few years.
Yeah, I don't know. So for the microtubule, I don't think, like for example, if we have faceplate data with the microtubule, does it mean that now we can do better with the undecorated microtubules to do this alignment? And we're really relying on kind of high-resolution features for that alignment. So, but we do have a faceplate. It works beautifully. Rado saw it, and we really have optimized. We can take 250 images before moving at 90 shift. It's really beautiful. And we, so that, it can happen in places other than Martin's Reed. It really works. So we have, in this case, a complex that is 300 kilodalton, but it has 2 domains that move, and we really have to sort, and take care of regions that are now 150 each. And it has made, a huge difference. And collecting the data really wasn't much harder. I think there's some optimization that can be done with fitting CTFs now. You have to be a bit careful. It's not totally bulletproof. But the data collection was not much more, and it was really nice. Oh, and this is regular grades. No gold, no silver, no platinum.
Okay, are there any more questions, please? Okay, if not, thank you again, Eva.